The numbers that shouldn't exist. Have you ever seen numbers that were completely correct and still led to the wrong conclusion? It sounds impossible. After all, numbers don't lie. So how can accurate data tell a misleading story? Imagine you need to choose between two hospitals. Hospital A successfully treats 90% of its patients. Hospital B treats only 85%. The choice seems obvious. If someone you love needed treatment, Hospital A appears to be the better option. But then researchers decide to examine the patients more carefully. Instead of looking at everyone together, they separate the cases into two groups: patients with mild illnesses and patients with severe illnesses. Now something extraordinary happens. Among patients with mild illnesses, Hospital B actually has the higher success rate. Among patients with severe illnesses, Hospital B performs better again. Wait a second. If Hospital B is better with mild cases and better with severe cases, how can it appear worse when we combine all the patients together? That shouldn't be possible. Yet every number is correct. Every percentage has been calculated perfectly. No mistakes, no hidden data, no manipulation. So where did the contradiction come from? This strange phenomenon has a name: Simpson's paradox. It's one of the most surprising ideas in statistics because it reveals something most people never expect. Sometimes, combining information can hide the truth instead of revealing it. At first, this feels like a mathematical trick, but it isn't it. Scientists encounter Simpson's paradox in medicine. Economists find it in financial reports. Sports analysts see it in player statistics. Researchers even struggle with it when training artificial intelligence. Again and again, perfectly accurate numbers produce completely misleading conclusions. Not because the data is wrong, but because we're looking at it the wrong way. And that's what makes this paradox so fascinating. It doesn't challenge mathematics. It challenges the way we interpret mathematics. Before we uncover how this happens, let's look at one of the most famous real-world examples ever recorded, a case involving one of the world's leading universities. At first glance, the numbers seem to prove discrimination beyond any doubt. But when researchers looked deeper, the entire story changed. And that's where Simpson's paradox truly begins. The university that seemed guilty. In 1973, one of the world's most respected universities found itself at the center of a controversy that no one expected. The University of California, Berkeley, had just completed its admissions process, and thousands of applications had been carefully recorded. When researchers looked at the overall numbers, the results seemed shocking. Around 44% of male applicants had been accepted, while only about 35% of female applicants received an offer. The conclusion appeared obvious. Many people believed the university was discriminating against women. Newspapers reported the story, critics demanded answers, and the statistics seemed impossible to argue with. After all, the numbers were right there in front of everyone. But a group of statisticians wasn't satisfied with the first conclusion. Instead of looking only at the university's overall acceptance rate, they asked a different question. What if the admissions process looked different inside each department? So they separated every application by faculty: engineering, mathematics, history, literature, physics, medicine. One by one, they examined each department individually. What they found completely changed the story. In several departments, women were actually accepted at a slightly higher rate than men. In others, the admission rates were almost identical. Some departments appeared to favor male applicants, while others favored female applicants. There was no consistent pattern of discrimination across the university. Suddenly, the overall statistics no longer made sense. How could Berkeley appear to discriminate against women when many individual departments showed little or no difference at all? Both conclusions came from exactly the same data. No numbers had been changed, no calculations were wrong, no information had been hidden. The only difference was the way the data had been organized. Looking at the university as a whole told one story. Looking at each department separately told another. Which one was true? This wasn't just an interesting academic puzzle. It was a real-world problem with serious consequences. Decisions about fairness, discrimination, and public policy were being made based on statistics that seemed to contradict themselves. Somewhere inside those numbers was a hidden piece of information that almost everyone had overlooked. And once researchers discovered it, the paradox disappeared completely. In the next part, we'll slow everything down and examine data step by step. because the secret behind Simpson's paradox isn't it hidden in complicated mathematics. It's hidden in something much simpler, and once you see it, you'll never interpret statistics the same way again. Where the paradox is born now, it's time to solve the mystery. The first thing to understand is that the numbers were never wrong. Every percentage was calculated correctly. The paradox appears because we combine groups that are fundamentally different. Let's imagine a much simpler example. Suppose there are only 2 university departments. Department A is easy to get into. It accepts 80 out of every 100 applicants. Department B is much more competitive. It accepts only 20 out of every 100 applicants. Now imagine that most male students apply to Department A, where admission is easier. At the same time, most female students apply to Department B, because they're interested in subjects that happen to be far more competitive. Inside each department, men and women are treated equally. Their acceptance rates are almost identical. In fact, women might even have a slightly higher success rate in both departments. But here is what happens. Since most women applied to the more competitive department, their overall acceptance rate becomes lower when all the applications are combined. Nothing unfair happened inside either department. Nothing changed in the admission process. The only thing that changed was how we looked at the data. This is the exact moment where Simpson's paradox is born. When different groups are merged into a single average, that average can hide the reality inside each group. Think of it like mixing 2 puzzles into one box. Each puzzle makes perfect sense on its own. But if you dump all the pieces together, the final picture becomes confusing. The pieces haven't changed, only the way they're organized. Statistics works the same way. An average is useful because it simplifies information. But sometimes, it simplifies too much. It removes the context that explains why the numbers look the way they do. That's why scientists rarely stop after calculating an average. They ask another question. What factors are hidden inside these numbers? Could age make a difference? Could location matter? Could experience, income, or education completely change the result? If the answer is yes, combining everything into one statistic may produce a conclusion that doesn't reflect what's actually happening. That's the real lesson behind Simpson's paradox. It is a failure of mathematics. It's a warning about interpretation. The numbers never lied. Our conclusion did. Once you understand that, you'll start looking at every chart, every headline, and every statistic a little differently. Because from now on, one question will always come to mind. What important information might be hidden inside this average? And once you begin asking that question, you'll realize that Simpson's paradox isn't just a lesson about statistics. It's a lesson about how easily the human mind can be fooled even when every single number is correct. You've been tricked by this paradox before. Now that you know how Simpson's paradox works, you'll begin to notice it everywhere, not because the world has suddenly changed, but because you've learned to see what was hidden before. Imagine reading a headline that says, "A new medicine is more effective than the current treatment." Most people would accept that conclusion immediately, but now you know to ask another question: more effective for whom? For younger patients, older patients, people with mild symptoms, or those with severe illnesses. If all those groups are combined into a single average, the final result might hide important differences. The medicine could perform better for one group and worse for another, even though the overall statistics suggest a completely different story. The same thing happens in sports. A player may appear to have the highest success rate in the league, but what if most of their games were against weaker opponents? Another player might have slightly lower overall numbers, while consistently competing against the strongest teams. Looking only at the average doesn't tell the whole story. Businesses face this challenge every day. A company may proudly announce that profits increased by 10%. Investors celebrate, but a closer look might reveal that one product generated all the growth, while several others actually lost money. The total looks impressive, but the details reveal a more complicated reality. Even artificial intelligence can be fooled by Simpson's paradox. An AI system may achieve excellent overall accuracy, yet perform poorly for specific groups of people. If researchers only look at the average performance, they might believe the system is fair when it actually contains hidden biases. This is one reason why modern AI researchers spend so much time analyzing data in smaller groups, instead of relying only on overall statistics. The lesson is surprisingly simple. An average is not the whole story. It's a summary. And sometimes, summaries leave out the very information that matters most. That's why scientists, doctors, economists, and data analysts always look beneath the surface before reaching a conclusion. They separate the data, compare different groups, and search for hidden variables that might completely change the outcome. Simpson's paradox reminds us that numbers don't become dangerous because they're wrong. They become dangerous when we stop asking questions. And that leads to one final idea. If even perfectly accurate numbers can fool us, how can we know when we're seeing the complete picture? That's the question we'll answer in our final part. The truth, hidden behind the numbers. After everything we've discovered, one question remains. If numbers can be completely correct and still lead us to the wrong conclusion, how can we know what is actually true? The answer begins with a simple realization. Data is never just about numbers. Numbers are only a representation of reality, and reality always has context. Simpson's paradox teaches us one of the most important lessons in statistics, science, and even everyday life. The way we organize information can completely change the story that information tells. A percentage by itself has no meaning without understanding what is behind it. A success rate does not tell us who succeeded. An average does not tell us who is being averaged. A final result does not always reveal the journey that created it. And this is why the most dangerous mistakes are not always caused by false information. Sometimes they are caused by true information that is missing the right perspective. Think about how often this happens in daily life. Someone says a person is unsuccessful because they haven't achieved something yet. Someone says a business is failing because 1 month was bad. Someone says a strategy doesn't work because the first results were disappointing. But what if we are looking at only one part of the story? What if there are hidden variables we haven't considered? Maybe the timing was different. Maybe the circumstances were different. Maybe the comparison itself was unfair. The human brain loves simple answers. We want a clear winner, a clear explanation, a single number that tells us everything we need to know. But the world rarely works that way. Complex systems are built from many different factors interacting at the same time. And when we ignore those factors, even intelligence can become a trap. Because the problem is not a lack of information. The problem is believing that the information we have is complete. This is why Simpson's paradox is much more than a statistical curiosity. It is a reminder of intellectual humility. It reminds us that being confident and being correct are not the same thing. A person can have accurate facts and still reach the wrong conclusion. A scientist can have perfect measurements and still misunderstand the phenomenon. A company can have impressive numbers and still be heading in the wrong direction. The difference is not the data. The difference is the interpretation. And perhaps that is the most surprising lesson of all. The numbers never betrayed us. They were simply waiting for us to ask better questions. Every chart, every statistic, every report contains a story. But sometimes the most important part of that story is hidden between the numbers. So the next time you see a percentage, a ranking, or a dramatic headline, remember Simpson's paradox. Don't just ask, what does this number say? Ask, what is this number hiding? Because sometimes the truth is not found by looking at more data. Sometimes it is found by looking at the data differently. And that idea goes far beyond mathematics. It changes how we understand science, how we evaluate decisions, how we judge people, and how we see the world around us. Because the greatest discoveries often begin with a simple moment of doubt, the moment when we stop accepting the obvious answer and start searching for the hidden story. If you enjoyed uncovering this paradox, stay with us. In the next episode, we will explore another impossible idea that challenges the way we understand reality itself, a phenomenon where something can be true and impossible at the exact same time.